Somebody tell me if it's not cool if I record it, but it's recording me. So we're going to talk about modular arithmetic. And as I promised, modular arithmetic is well, you can consider it sort of a shortcut in a certain sense. It's a way to sometimes look at a big problem in the integers or even a larger structure and reduce it down to something simpler. And we will do a number of examples that sort of illustrate the utility of this. So let me start off. So there's sort of two perspectives. There's two perspectives that I like to think about, and they're both kind of equivalent. The first one is, we say, for x and y integers, that x is equivalent to y mod n, where n is another integer, if x minus y is divisible by n. So, and another way to think about this, x and y are equivalent mod n is, if their difference is divisible by n, this is equivalent to saying x and y have the same remainder. When divided by n. So for example, 17 is equivalent to 3 mod 7. Because the difference in 17 and 3 is divisible by 7. And of course, they both give a remainder of 3 when divided by 7. And number two, equivalently, for those of you that have seen this kind of thing, you can think of this as elements of z mod n, or some people write z mod n. Now, some of you may have seen this, maybe not, so I'll sort of write down what I mean. So I think of the elements of z mod n as, I put the little hats over for a technical reason to distinguish this just from the ordinary zero, because this really represents the equivalence class, but you can think of it as an ordinary integer when I give you a caveat on the rules here. Notice that these distinct integers, 0, 1, 2, all the way up to n minus 1, are the possible remainders that you might get when you're dividing by n. You're going to get a remainder somewhere between 0 and n minus 1. And how do you add these things? Well, you add it like a clock. Think of this as 12 o'clock, 1 o'clock, 2 o'clock, and the 11th hour is n minus 1 o'clock. If you cycle around, you start it over again. So, for example, in Z12, if I took 10 bar plus 8 bar, well, you add these things just like ordinary integers, but now you say, well, whoops, 18 is too big, it's not in this mess. So you can divide it by 12 and take the remainder. So 10 plus 8 is 6 here, so to speak. And what you're doing is, this means you're adding something that takes remainder 10 upon division by 12 to something that takes remainder 8. And when you add them up, you'll get something that takes remainder 6. Okay. So that's a couple of ways that you can think about this. Now, here are some properties of modular arithmetic. I mean, this is the mathematician in me. I've got to tell you what this is. I've got to lay the law of the land down here. Rules for modular arithmetic. And this is, of course, not all the rules, but it's ones I'll use right now. First of all, this is an equivalence relation. So in other words, it functions very much like equality. Equivalence relations are things that function very much like equals does in the ordinary integers. So let me kind of go through this. One, A is equivalent to A mod n for any A, right? Because A minus A is divisible by n. I don't care what it is, right? And two, A is equivalent to B mod n implies B is equivalent to A mod n. This will be obvious when I kind of reword this for you. What this means is, this should be mod n. If A minus B is divisible by n, then multiply that by a negative sign, B minus A is divisible by n. Right? And also we have transitivity. That is, A is equivalent to B mod n. And B is equivalent to C mod n. Then A is equivalent to C mod n. And this is the only one that really requires any kind of observation. What this means is A minus B is a multiple of n. And what this means is B minus C is another multiple of n. So if you add these two up, add these equations up, you get A minus C is K plus L times n. And so A is equal to C. So what that means is that this notion of equivalence functions very much like equals. And now I'm going to give you some other stuff here, some other properties that indicate that this behaves very much like ordinary addition that you're used to, and multiplication. Here are some basics here. Number one, if K is an integer and A is equivalent to B mod n, then A plus K is equivalent to B plus K mod n. This is easy to prove because if A minus B is divisible by n, then this thing minus this thing is divisible by n because the K drop out, right? If, so I'm going to put a couple here together, if A is equivalent to B mod n and C is equivalent to D mod n, then Roman number one, A plus C is equivalent to B plus D mod n. And number two, AC is equivalent to BD mod n. And so, three, if A is equivalent to B mod n, and K is a natural number, or zero, well, actually, I'll take that. Then A to the K is equivalent to B to the K mod n. So if two things are equivalent mod n, then their powers are also equivalent mod n. That's because A minus B is divisible by n, and if you have AK minus BK, that's got a factor of A minus B in it. More generally, P of A is equivalent to P of B mod n, where P is a polynomial. with integer coefficients. So let me illustrate what I mean by that last mark there. Maybe we'll kind of do this in action. So for example, well, actually, it's so much easier. 1 is equivalent to 8 mod 7. Right? Because 1 minus 8 or 8 minus 1 is a multiple 7. So let P of X be some polynomial with integer coefficients. Who cares? 2x squared minus x plus 5. What this means is I get some number when I plug in 8 to this. I get an easier number when I plug in 1 to this, but they should be the same mod 5. Let's see what I get when I plug in 8 here. I get 64 times 2 is 128, minus 3 is 125. And when I plug in 1, I get 6. I get 6. So if you look at P of L minus P of 1, this is 125 minus 6, which is 119, which is a multiple of 7. So P of 8. So P of 8. In this case, 7. That's an illustration. 7. That's an illustration. Okay. Any questions so far? So far, so good. Okay. So all these properties endow this with a ring structure, and in fact, I'll write this ring as C mod n. So let's look at this. Let's look at a couple of examples here. So think of this as the set of remainders that you can have mod 5, right? So when you divide by 5, you're going to get a remainder 0, 1, 2, 3, or 4. And you multiply and add just like you do in the ordinary integers, right? 2 bar plus 3 bar is 5 bar, which is 0 bar. 3 bar plus 3 bar is 1 bar. 3 bar times 4 bar is 12 bar, which is 2 bar. Okay? So let me point out that if you look, notice that 2 bar times 3 bar equals 1 bar. And 4 bar times 4 bar, 16 bar, which is 1 bar. 16 bar, 1 bar times 1 bar. Notice also that 1 bar times anything is the identity. The 1 bar performs very much like the ordinary integer 1 performs the integers, right? When you multiply it by anything, it leaves it alone. Right? Oh, Renzo, do you have a question? If anybody has a question, feel free to speak right up. But notice what happens. All of these elements that are not all have an inverse, right? So you can think of 3 as sort of like 1/2 in this rate, and you can think 2 as 1/3, right? Because basically they multiply together to be 1. You can think of 4 and 1/4 as being the same thing in this rate, correct? This is kind of interesting because notice everything that is non-zero, you can multiply something by it and get 1. Of course, 0, there's nothing you can multiply by 0 to get 1. Now we can see 6. These are remainders that you might get upon multiplication by, or I'm sorry, upon division by 6. Notice that there's some different stuff that happens here. Notice in this case, 1 bar times 1 bar is 1 bar. So 1 has an inverse, namely itself. 1 times anything is in. 5 bar times 5 bar is 25 bar, which is 1 bar. But notice there's some strange things afoot here. 2 bar times 3 bar is 0 bar. Now that's something that's a little unusual. You don't see in the ordinary integers. I can't multiply 2 non-zero integers and get 0, but I can here. 2 bar times, oops, I'm sorry, 4 bar times 3 bar is 0 bar as well. And this one's even more kind of bananas. 3 bar times 3 bar is 3 bar. You multiply it by itself and it doesn't change it.
Jim, we have a request to zoom in on the board.
Adam, do you want to control my camera? Is my camera off or something? Okay.
Here.
Oh, okay, I got you. Oh, so you want to do that for everybody? That would be awesome.
Sure thing.
Okay, everybody with me so far? So this is a couple of contrasting things here, right? Here you've got non-zero elements multiplied by 0. You don't have this here. Let me give you a follow-up thing. So let me give you a quick definition. We say K bar is a unit if there exists M bar such that K bar M bar equals 1. We say it's a zero divisor. K bar is a zero divisor if there exists L bar such that, well, let me be clear here. If there's a non-zero L bar such that K bar L bar is 0. So over here, right here, 2 and 3 and 4 are zero divisors, and these 6, and these 1 and 5 are units. 0 is a zero divisor technically because you can multiply by a non-zero thing to get 0. It's just kind of a silly. Here is a theorem. In Zn, you always have one or the other. In Zn, every element is either a zero divisor or a unit. And in fact, I'm going to show you why that's true because it's very short. I won't even need the rest of this board. And it also illustrates something. Proof, so to speak. Suppose A is not a zero divisor. That means you can't multiply A by anything that's not 0 and get 0, right? So it's cool like that. Consider all powers of A squared, A cubed, A fourth, and make this list forever and ever. These are all elements of Zn, right? Maybe this is K bar and this is K squared bar, or whatever that turns out to be, K cubed bar, etc. This is a list, and it is an infinite list, right? Because these powers go forever. It is an infinite list of elements that are in a finite set. There's only n different things these can be. Everybody agree? So if I have an infinitely long list and only n different things it can be, what can you tell me must happen?
At least one must appear infinitely many times.
Anybody guess? Well, so I've got an infinite list, but I've only got finitely many slots to put it in. There has to be repetition. Everybody agree with that? So there has to be some power of this in K such that N is a bad choice. I'm sorry, MK, such that A to the M is A to the M plus K. So that is to say, you have a power that appears and then it appears later, right? There has to be repetition. This implies AM times 1 minus AK is equal to 0. Well, A is not a zero divisor, right? And so that means that you can't multiply by anything non-zero, get 0. So you can pull 1 power of this off. Now A to the M minus 1 times this is 0, but A is a zero divisor. And at the end of the day, you must conclude that A minus 1 minus A to the K is 0. Therefore, A to the K is 1, which is A times A to the K minus 1. So if it's not a zero divisor, it's a unit, because I found out something that I can multiply by and get 1. Everybody okay with that? Questions on that subject? Okay, let me give you one more theorem here that will be useful, and then I want to give you an open problem. Theorem. All non-zero elements of Zn are units if and only if N is, anybody want to guess?
Prime number.
Yeah, I see y'all out there lip syncing like you're Milli Vanilli.
Prime number.
And so if you got it, prime. Excellent. That is correct. When N is prime, then all non-zero elements of Cn are units, and the converse holds. This is worth showing. So this, if N is not prime, then we can decompose N as A times B, where A and B are strictly less than N. Therefore, in Zn, A bar times B bar is 0 bar. And so neither A bar nor B bar is a unit because it's zero divisor. On the other hand, suppose N is prime and let A be in Zn, but not 0. So pick a non-zero element of Zn and it's prime. I'm going to be sloppy. Well, actually, let me call this A bar. There exists, well, so in particular, you can think of the representative of A because A bar is not 0, so it's not a multiple of N, so it's somewhere strictly, so if you pick the remainder has to be at least 1, and actually I should say strictly less than N. It'd be strictly between A and N. Notice that the greatest common divisor of N and A is equal to 1. That's an important observation because N is prime. And so the greatest common divisor of a prime in anything is equal to prime itself at 1, but the prime can't divide A in this particular case. So it has to be 1. So there exists X and Y and Z such that nx plus ay equals 1. Those of you that have my algebra class, I beat this to death. The greatest common divisor is a linear combination of the two elements, right? Now reduce this mod n, and you get, that's 0, because that's divisible by n. A bar times y bar is 1 bar. And there you go. Any questions on that? Okay. In fact, I'm going to take this a step further. ZP, and in fact, more generally, ZP to any power has a primitive root. What do I mean by that? I mean an element whose powers sweep through all,
Excuse me, Dr. Quickendall.
all units of ZP or ZP to the M.
Excuse me.
Now, of course, in ZP, that's going to be everything that's not here. So let me give you an example to sort of illustrate what I mean.
Is my mic working correctly? Or
If you look at the powers of 2, two cubed,
It's
which
not a
is
recording, but he can't seem to hear us.
And
Try posting him in chat.
4,
He'll get
which
around,
is 6, which is 1.
get around to reading them when he looks back at the screen again.
And then if you take another power, it sort of starts all over again, right? Example. Z7. If you look at this one, if you look at 2 bar squared is 4 bar, 4 bar squared, 2 bar cubed is 8, which is 1. Notice what happens with 2 here. It goes 2 squared is 4, 4 squared is 8, which is 1 minus 7, and now it starts over. This is not a primitive root, because its powers don't sweep out all the non-zero. Notice I'm missing, I'm not missing 1, but I'm missing 3, 5, and 6. But there is a primitive root. Notice it picks up 2 in the second jump. That probably means it's going to take 6 cycles. 3 cubed is 27, which is 6. 3 4th is 81. Is 4. 3 to the 5 is 243, which is, so it's 5. And 3 to 6 is, and then it starts over. So for C mod 7, 3 is a primitive root, and it goes through all the powers. Let me give you another one. One more example. Let's look at C mod 25. And I am actually going to take the pain of writing this down. I'm going to write down in what I think is kind of a suggestive way. Forgive me for not putting the bars on top of this, as I just want to save time. 6, 7, 8, 9, 10, 11, 12, 13, 14, 21, 22, 23. Here are the elements of C25 without the bars on. Notice this is sort of Z5 along the top, the original Z5, and they've sort of grown roots down here. Notice in this column, everything, these are different mod 25 because, for example, 6 minus 1 is 5. It's not divisible by 25, but it is divisible by 5. So all of these stalks collapse down to the single thing at the top, mod 5. For mod 25, they spread out. Notice in Z mod 5, these are the units because 5 is a prime. Their stalks are also units in 25. And these are all the zero divisors. And in fact, there's something even stronger called nilpotents. Notice when you square any of these, you get 0. Because when you square 5, well, 5 squared has a factor of 25, so it's equivalent to 0. So any of these squared is 0. 2 is actually a primitive root, mod 25, and I'll run through it here. 2, 4, I'll do this quickly without the thing. So 2 is actually a primitive root. It should run through all 20 of these. Maybe I'll do half the computations and sort of illustrate why it should go all the way through. 2, 4, 8, 16, 32, which is now back to 7, 14, 28, which is 3, 6, 12, 24. I've gone 10 of the 20. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Notice this power of 2 is actually -1, because -1 is -1 is the same thing as 24 by 25. That indicates to me when I square this, I'm going to get 1, so it should be another 10. So actually, you can check this yourself. This goes 2, 4, 8, 16, 7, 14, 3, 6, 12, and 24. Now it will jump back and go through the other columns. The next one will be -2, which in this case will be -2, which will be I guess 23, and so forth. Notice it jumps in the columns in the same order that Z mod 5 did, and it'll read up all these things. This is a primitive root. So I promised I'd give you an open problem. And here it is. Conjecture. For infinitely many primes, two is a primitive root. For Z. Not even CP to a power to CP. This is unknown and has been unknown for, I think, over 200 years, actually. The answer to this appears to be true, but nobody knows how to solve this one. So if any of you figure this out, be sure to let me know so I can steal it. This is Fortune and Glory if you want to try to take care of that this weekend. So let me do some applications now. So this will be, by the way, I'll give you one other fact here. Notice that 2 is a primitive root in Z5. That was the first example we went through. It also turned out to be a primitive root on Z25. So the question is, you might ask, well, so if you find the primitive root up here at the top stall, primitive root of the Z5 or ZP in general, does that work to be a primitive root in Z mod P squared in the next step? And the answer is not always. But if it works at ZP squared, it will continue to work for all other higher powers. Doesn't matter. And I should also point out, I don't know, I thought I said it, but maybe I didn't. For the primitive root to have, to go through all the units in C mod P at the end, you need P to be an odd prime. So let me give you some examples. Some interesting examples. I'm going to call this something. Z5 has I. You all have all encountered I, right? It's an old friend. You have it in complex analysis or whatever. I is the square root of -1. Notice in Z5, 4 is equivalent to -1 mod 5. And 2 squared is equivalent to 4 mod 5. So 2 functions like I. So actually in Z mod 5, you consider this, this little structure here. 2 basically functions like I, because when you square 2, you get 4, which is actually -1. And in fact, this is true not just 5, this holds for E prime P equivalent to 1 mod 4. So for example, 5 and 13, there'll be something, so for example, in Z13, 5 squared is equivalent to 12, isn't it? Yes, which is equivalent to -1 on 13. So in Z13, 5 is your I. That's kind of weird, right? Because, you know, they're one of the great sort of mathematical holdups historically was, well, there was a big holdup on negative numbers. People were like, oh, I don't believe in negative numbers. And then there was also a holdup about imaginary numbers, which part of the problem with imaginary numbers is they are so unfortunately titled. But here you have things that can square to negatives all over the place in these. Here's another one. Let me give you kind of a background question. If I have a polynomial, well, let me give you a specific. X7 plus 3x6 plus x squared plus 2. Suppose I have that polynomial, right? One of my personal favorites. Now, my question is this. How many roots can that have? What's the most number of roots? That is correct. 7 is the most number of roots. How many of you are familiar with that old chestnut, right? Degree 7 polynomial can have the most 7 roots, right? Consider Z mod 32 and polynomial x to the 5th. Now, of course, x to the 5th can have at most 5 roots, say in the rational numbers or real numbers. And in fact, it's got one root that has, it has one root of multiplicity 5, namely 0. In Z32, this has 16 roots. There are 16 different numbers, and only 16 you can plug in to get you 0. That's kind of weird, isn't it? And basically, it's all, and here's what they are: 2 bar, 4 bar, 6 bar, oh, and of course 0 bar, 8 bar, all the way up to 30 bar. Because every one of those is an even representative. And when you take an even number to the fifth power, it will have a factor of 32. So this polynomial, this fifth degree polynomial, has the wacky 16 solutions. So there's some things that are a little bit different than what you might be used to. Let me give you another couple of applications, including we'll finish off that problem. So here's one example. Show n cubed minus n is always a multiple. This one's kind of an easy one, and you don't really need modular arithmetic, although that's essentially what you're doing when I prove it. This is actually an old chestnut. If you ever teach like a proofs course, this is kind of a classic one when you're doing induction. What you try to do is you're getting people warmed up for induction, you get them to do this, and they prove for n equals 1, and they do the inductive hypothesis and all that. There's actually an easier way to do this. N cubed minus n is equal to n times n squared minus 1, which is n minus 1 times n plus 1. And notice n minus 1 times n plus 1 is equivalent to 0 mod 3. Because what you have here is 3 consecutive integers, right? So if any of these are 0 bar, then you're done. So that means that's got to be 1 bar, forcing that to be 2 bar or 3 bar, or this has to be 2 bar, forcing that to be 0 bar, right? So no matter what you do, this is 0. In fact, this runs through all the elements of Z mod 3 and Z. So that means that no matter what you try to plug in for n, you will always get a multiple of 3. Here's another one. And this one actually shows sort of one of the most powerful mods there is. And that's 4. Let's see what's my number here. Example. Show 4851 is not the sum of 2 squares. Many numbers are the sum of 2 squares. In fact, any square is the sum of 2 squares. 25 is 5 squared plus 0 squared, right? But there's lots of other ones, like 2 is 1 squared plus 1 squared, and 25 is 3 squared plus 4 squared. 169 is 5 squared plus 12 squared. And actually, there are lots and lots of things that are sums of squares. For example, every square is a sum of square. Every square plus 1 is a sum of 2 squares. Every square plus 4, and so forth and so on. How can you tell? I mean, I don't know about you all, but the square root of this thing is like, it's like pushing 70, right? So I don't want to go through and square a whole bunch of smaller stuff and try to go through it exhausted. Here's what you can do. Suppose x squared plus y squared is 4851. Suppose, just for giggles, that I can write this as a sum of 2 squares. Reduce mod 4. So all my properties say that I can do this. Well, mod 4, what is this mod 4? If I divide this by 4, what's the remainder? It's 3. I mean, you can only do 0, 1, 2, or 3. It's not even, so it's not 0 or 1, or I'm sorry, it's not 0 or 2. And it turns out it's 3, right? Now, I've gone from testing a lot to just testing a little, because X and Y only have 4 possible inputs, and we square it, it gets less than that. So if you look at X and X squared, well, mod 4, then the square is 1, 0. So each one of these can only be 0 or 1, right? Because all the squares mod 4, everything squares to either 0 or 1. Pair of zeros doesn't work, a 0 to 1 doesn't work, pair of ones doesn't work. No solution. So if there had been a solution up here, there would have had to been one down here. I only had to check a very small number of things. Bang, no solution, no solution. This is much, much, much easier than trying to tackle the problem as it's written. Here's another one. So I'm going to get to the challenge problems that I had sort of in the teaser problems I had in my advertisement. Here's the one. Does this have any solutions? It's hard to tell, isn't it? Right? I want to square something minus 10 times another square. Can I make that balance to 3? It's not clear because maybe I'd square some big number X and then square a smaller number, a little bit Y, and maybe it works out, maybe not. Let's do the same thing here. Let's reduce mod 5. Why 5? Because 5 divides 10, and that's going to take this out. That's really what I'm about, is destroying things here, making it as simple as possible. I reduce this to the equation x squared is equal to 3 mod 5. Is this solvable? 0, 1, 2, 3, 4. What are the squares, mod 5? Let's look. 0, 1, 4, 4, 1. There is no 3 over here, so there is no solution. So accordingly, there is no solution here. Because if there had been X and Y, it would balance this equation here. It can't happen. Now this one is amazing because there are infinitely many things to try here. Infinitely many. How do you ever know when you're exhausted and done? I don't, right? But when I pass to this reduction, now this reduces to an equation where I've only got 5 things to check. That's it. None of them work, I'm done. So that shows you that this thing is, that modular arithmetic has some serious power. And so, since I've got 1 minute left, I will leave you with my friend Jenny. The last teaser I had was this one right here. Last 2 digits. 5,123 to the 8675309 power. You know, I amuse myself preparing this by going online and finding there's like lots of super geeks out there that build these calculators online that will, it's actually kind of impressive, that will compute a lot of digits very quickly. I was kind of impressed by it, but they couldn't handle this. This is out of control, right? And in fact, one reduction, so when I look at the last 2 digits, I want to go here, mod 100. Because mod 100 allows me to forget about every digit that is the hundreds place and beyond. And so this reduces my problem to 23 mod 8675309. Right? So I've reduced it a little bit more. But I tried this actually on those big calculators and they wouldn't work either. And I found a bigger calculator that did sort of work, but it gave me scientific notation. There's actually something like 32 million digits in this, right? And so they only gave me the first 7, and they were the first digits, not the last, so that didn't help much. So how are you going to do this? Well, 100 is 5 squared times 2 squared. So figure this out. What the answer is mod 4 and mod 25, and glue it back together for mod 100. Let me tell you what the answer is. Yeah, that's what I got. I got last 2 digits are 6, 3. See if you can figure that out using some of these techniques, or if nothing else, what you could do is you could take 23 mod 100 and see how many iterations it takes to repeat itself. And in fact, you will find that it takes 20 iterations. And so once you've got that, every 20 iterations this repeats. Now you've got 23 to the 9, as opposed to 8, 6, 7, 5, 3, or 9, which is much easier. But see if you can figure that out. If you got any questions, let me know. Any questions? You guys have been chatting it up, which is really kind of cool, actually. Let me ask you all this, because I really want to know for proceeding further in this. Can you all talk to me, or will you just try to be nice and quiet?
Well,
Can
we've been
anybody
trying.
talk to me?
We've been trying, but we don't think you can. No.
Dakota, are you trying to talk to me?
Yeah, there's been some questions.
Yeah,
but,
I can't hear you on my end, and I'm sure that's some stupidity on my part. So anyway, yes, yeah, I can't hear you. So I don't see anything on this. So yeah, the last person left something funny in the room too. I have to do weird stuff, so I'm not too surprised. So I am looking. If you've already asked something in the chat that I didn't deal with, ask it again, and I'll repeat it, try to answer it. Okay, if you guys took care of them in the chat, good. Has anybody got anything else? Okay, well, if there aren't any other questions, I appreciate y'all coming out. I hope you got something good out of it. Next week, we will have Freeman Slaughter, who always comes up with like interesting stuff to talk about. It's probably going to be about chess, but we'll send along an announcement later. Other than that, y'all have a good weekend, and I will see you all soon.